All right, so like, have you ever thought about what makes things like what makes a rubber band stretchy, but a rock? Well, a rock. It's all about matter, right? And that's what we're diving deep into today, the stuff that makes up, well, everything. We're taking a look at this excerpt from a science textbook, Matter in Our Surroundings, and let me tell you, it gets pretty wild. So first things first, the book just comes right out and says it, everything, and I mean everything, is made of these like crazy tiny particles. We're talking smaller than small, like, those potassium permanganate crystals, the ones that stain your fingers if you just look at them wrong. The book uses this example. Imagine dropping like a couple of those crystals into a giant swimming pool.
And those few tiny crystals can turn that whole pool this vibrant purple. It really shows you just how incredibly tiny the particles they're made of must be.
That's insane. It's like, boom, the whole pool is purple.
Oh.
But those tiny particles do more than just make cool colors, right?
Oh, absolutely. They're the key to understanding so much about how things actually work. Like, think about how you can smell cookies baking from all the way down the hall. Those scent particles, they're not just magically appearing in your nose, they're spreading out through the air from a high concentration, your oven, to a lower concentration.
Your nose. So those cookie-scented particles are basically on a mission to explore, even if it takes a while. That's what diffusion is, right?
Exactly. And the rate at which they explore, that depends on a few things, like temperature. The hotter it is, the faster those particles move and spread that scent.
Which is probably why cold cookies just don't smell as good.
Yeah.
But okay, if everything is made up of these tiny particles constantly moving, why aren't we like a giant blob of moving particles? What holds it all together? The textbook gets kind of fun here. They talk about this human chain to explain how particles attract each other and like stick together.
Right. Imagine a bunch of people all linking arms, forming this super strong chain. That's the force of attraction holding those particles together in a solid.
Yeah.
Trying to break those bonds is like, well, trying to break through a human wall. It takes serious energy.
So solids are like that, like super strong human chain. But what about liquids? Are those particles like holding hands?
Yeah, exactly. Still connected, but with more freedom to move around. The bonds between them are weaker than in a solid.
So they're still attracted to each other, but they can like flow and stuff.
Right, they're doing a little molecular dance, which is why liquids can take the shape of whatever you put them in.
So in my glass of water, those particles are having a little party.
Pretty much. Now imagine those partygoers suddenly got a burst of energy and started like bouncing off the walls. That's gas.
Whoa. Okay, so the forces of attraction in gases are like way weaker.
So weak that the particles are basically off the chain, zooming around, bumping into each other in their container, and all that bumping around, that's what creates pressure.
Wild. Solids, liquids, gases, got it. But hold on, ice. You put an ice cube in your drink, it floats. Why doesn't it sink?
Density. Basically, how tightly those particles are packed together, ice is actually less dense than water.
Wait, really? How can something be less dense as a solid than a liquid?
It's about how those tiny particles, those molecules, arrange themselves. When water freezes, those molecules spread out, forming a crystalline structure. So ice takes up a bit more space for the same amount of stuff, which means lower density.
So it's not just about what the particles are, but how they're like arranged through vibes.
Exactly.
Okay, so temperature. We know heat can melt things. Ice cream on a hot day, you know the deal. But what's happening to those particles?
Temperature is all about energy, more heat, more movement. When you heat a solid, those particles vibrate so much they break free from their rigid structure and boom, liquid state.
But here's the thing that always gets me. When you melt ice, the temperature stays the same, even with more heat. What's going on there?
Latent heat. During a change of state, like melting, that heat energy isn't increasing the temperature, it's breaking the bonds between particles.
It's working behind the scenes.
Exactly. And that latent heat thing works both ways. When water evaporates, it takes energy from its surroundings. That's why a steam burn is so much worse than hot water. It's not just the temperature, it's that latent heat being released as the steam condenses.
So that's why sweating cools us down.
Yeah.
Built-in AC. But okay, we've talked about solids, liquids, gases, temperature, all that. What about evaporation? Like puddles dry up even when it's not hot out.
Right. Evaporation isn't just boiling. It happens all the time at different temperatures.
So if you've ever wondered where those puddles go, or why your clothes dry faster on a windy day.
You're already thinking about the factors that influence evaporation. Heat, surface area, humidity, wind, all of that matters.
Okay, so break it down for me. Surface area, how does that even work with evaporation?
Think about like Spreading out your laundry versus bunching it all up. The more surface area exposed to air, the faster the water can evaporate. More escape routes for those molecules.
Makes sense. So a bigger puddle will evaporate faster than a little one.
Well, not necessarily. It's about the surface area exposed to the air, not just the total amount of water.
Right, right. Okay. So what about humidity? I swear, my laundry takes forever to dry on a humid day.
Because humidity is basically how much moisture is already in the air. High humidity means the air is already full of moisture, so it's harder for more water to evaporate into it.
So drier air, faster evaporation. Got it. What about wind? How does a breeze dry things faster?
Right.
Like the wind is just like carrying those water molecules away. So the
Yeah.
drier it is, the windier it is, the faster things dry. It's an evaporation party.
Exactly. And knowing this isn't just, interesting trivia, it's actually super useful. Like, think about how we dry clothes or how farmers figure out when to water their crops.
It's all about evaporation. Who knew? This whole deep dive, it's really shown us how these like invisible particles, they make everything around us. And it's not just about knowing how things work now, but like what we could create in the future.
Yeah.
Imagine if we could like build things with specific properties just by like messing with these tiny particles.
That's what nanotechnology is all about. Creating materials that are like crazy strong but super light, or fabrics that, change depending on the temperature.
Whoa. Self-drying clothes, that'd be amazing. But we're talking like bigger than clothes, right?
Yeah.
What about like medicine or how we make energy?
Oh, yeah. The possibilities are huge. We could create super targeted drug delivery systems or like solar panels that capture energy at like the smallest level.
So crazy. We started with rubber bands and rocks, and now we're talking about like the future of everything. And it all comes back to those tiny particles. So next time you see like an ice cube melting or a puddle drying up, remember those tiny particles doing their thing? It's a whole hidden world out there, and it's responsible for, well, everything. And that's it for this deep dive into matter. Keep those questions coming, and we'll see you next time.